Okay, I was muted. Yeah, it was that simple. All right, so hello everyone, and welcome to a new final project presentation ceremony. Today we have Emeric Arhant, one student that has just finished his final project. He's going to be presenting the project about TicTacToe robot. And yeah, so just before getting started, remind everyone here in the YouTube live stream that in case that you have any questions for Emeric about his project, so you are free to share them here in the YouTube chat, as we are going to be doing a brief Q&A session after the presentation to make some questions for Emeric to clarify them to us. So yeah, let me not waste more time and say hello to Emeric. Hello, Emeric.
Hello, can you hear me well?
I think so. I can hear you here. So
Okay, perfect. Okay.
So yeah, the audience is all yours.
Okay, thank you very much. Let me share my screen and I'm gonna get started. Okay. Can you see my presentation correct?
Yes, we can see it.
Okay. Okay, well, hello everyone. Here I am. My name is Emeric Arhant. I've just finished the construct masterclass and I'm gonna present my final project, which is called TicTacToeBot. So what is TicTacToeBot about? The rules are simple. There's a robot arm, a game grid, and a camera. And the goal is to make the robot play the game tic-tac-toe against a human, using the camera to find out what is going on in the grid and figuring out what the best move is for the robot. So the main tools I use for this project are obviously ROS2, which is the main framework that we studied at the master class at the construct, and also two tools, one for perception, which is OpenCV, and the other one for moving the robot, which is MoveIt 2. And also for simulation part, I did a lot of testing in simulation. I used RViz for visualization and Gazebo for simulation. And there's also a web application to control what the game is going to be like. And I used a framework called Vue.js for this. And I also made there are also some assumptions for this project to make it feasible in the amount of time that I had. The first part is the fact that the package control the robot is already set it up. So the things that I had to do in order to make the robot move was just interacting with this pre-made package. Also, most of the parts of this of the real environment, so the camera and the board, are fixed. The positions are fixed, and by extension, the grid lines positions that are going to be traced by the robot on the grid, the tic-tac-toe grid lines, they are also fixed position in my project. And the variables that I had to battle with were the varying lighting conditions in the real lab in Spain, and also the drawing variability of a human being, and also sometimes the robot. So in a nutshell, an overview of what my project structure is. It's mainly 4 parts in the computation part. There's an order part. It's going to interact with a perception part that is going to query the game board, find out where the grid is, where the shapes are, and then send the current state of the board to another part called best move, which is going to figure out what the best move is for the robot on the current game grid. And it's going to answer the order part with where the robot should go this time. This order part is going to now finally ask a trajectory part to move the robot where it needs to move. And the robot will make the move and draw the shape where the best move for its current turn is. And also there's a web application part where you can see what the game looks like in live, and also what the camera sees, and also what the camera sees after the computer vision pipeline. So where the grid lines are and where the shapes are, and also you can control the robot using this part of the web application. Yeah. So this is what it looks like in simulation. So this is RViz to visualize. The simulation is here. And here the part of the web app where the robot is currently drawing the grid. The robot is now playing cross, so it's gonna finalize the drawing of the grid, and I'm gonna spawn the grid. It's gonna place a cross, and I'm gonna spawn a cross, and then the human, which is currently me controlling the robot because it's for testing, I spawn a circle, and then the robot is going to spawn a cross where he found the best move, and so on and so on until the game is done. So this is what the simulation looks like. And also here you can see what the best move part I'd put it for where the robot should play. So yeah, there you go for a simulation. Now let's move on to a real setup, and let's see what this robot is capable of doing. So you should see now my...
Okay, so we are going to connect now to the real robot, Emeric?
Yeah, yes.
Okay.
Oh, yes. So you should see the my masterclass.
Yes, we can see it. We can see
okay.
it. The project view.
Okay, so here's the robot live on the left. I already launched all the web part and all the part that's running for the robots to move. And you can see there live. Currently it's just a camera live, and we're gonna, so if, let's start by, maybe the robot could start this game. So you can choose what the robot plays here, and then the human will have to play a circle. On the left, you can see, so everything I talked about, you can go to all the positions you want, the robots. So 4 is the center, and 8 is here, etc. You can put it in standby, which is just above the clear button of the grid. You can go to home, which is just retracts. Draw grid, draw circles, draw cross, and clear the board when the board is full. So let's start the first game. The robot is going to play cross, and I'm just going to click this button to make him trace the grid and then place its first cross on the grid. And then we'll be able to see afterwards what the perception system is seeing. So here it goes, drawing the grid. You can see also live the robot with a little bit more frame rate here. Okay.
Yeah, so this is the view from the camera, actually, right?
Yeah.
From the perception, the camera that you use for perception, let's say.
Perception camera here and overview camera here, in which we can see the perception camera here. Yeah. So now he's gonna place its first cross. It's always cross that's starting, TicTacToe. And then if everything goes well, we're gonna be able to see what the perception pipeline could see. Okay, so here we are.
Okay. So now it would be turn for the human to play?
Now would be turn for a human, yeah. So if someone wants to play against the robot and place a circle where he wants,
I think Roberto is around there. We can see his shadow, so.
Okay, perfect. Okay, thanks a lot.
That one was a tricky one by Roberto because he placed it near one of the grid lines.
Yeah, nope. I think it's struggling to get the circle. It's a bummer, yeah.
Let's see.
Yeah, let's wait a bit. Okay, I think he found it. Nice, 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 nice. Okay, cool. Thanks for the correction of the circle.
So what do you think it was? It was the lightning, or the line was too thin, or it was because it was close to the grid, or?
I think the close to the grid is causing problem because my my perception. I'll talk about it afterwards,
Okay.
but the perception is merging the contour, which I find for a circle, it's merging it with the grid line, and then it jams the shape detection.
Okay. Okay. Okay.
Sorry.
So let's ask Roberto to try to put it in the center. Next move.
Yeah, if he wants. Maybe, yeah. Thanks. Okay, I think you should get this one. Yeah, so thanks, Roberto, for letting the robot win. I
Well,
think
I mean,
we
maybe
can.
he was outsmarted by the robot. We cannot know.
Yeah. Okay, so yeah, I think thanks for playing against the robot. I think okay, so we have the statement cross wins, crosses robots, so yeah, robots wins. And we should be able to do another game, maybe with a human playing cross.
Okay, let's switch
So
sides.
I'm gonna clear. It's gonna clear the board and clear the web app as well. Let's switch back to roll camera. Okay. And then let's switch. So human will play first. And if I start the game, the robot will place the grid first and then wait for the human to make the first move. Okay. Some of the lines are a bit, and this is consistent. The lines are a tiny bit curved on the below side, on the downside, and it's because I think the position of the robot when it's placing the grid lines, it's a tiny bit too low, and that's why it's a bit warping the pen that makes the lines. But
Yeah, makes sense.
yeah. Okay, yes. So yeah, Roberto, feel free to make the first move wherever you want. So it's a cross. Thanks. Okay. I think
Oh,
yeah, that's an issue. I think the robot found yeah, yes. Okay, so it's wrong, but it's right, I guess. It found a cross here, I think, because the this is a thing that I would have had to account in my code that sometimes when the human or someone comes into the frame, it jams up a bit the perception because I didn't update the logic to make it stop in the right moment. So I think he thought there was a cross right here, and then he played the best move in the middle where he thought it was nothing because it takes the first one of the first valid outputs of the perception system and then output the best move from that. So if there's a cross here and he wrongly thinks there's a cross here, he's just gonna draw a circle wherever it's best. But then it got back. I think it since the cross is in the middle here, even if there's a circle around, he's just gonna find. I will explain in detail later, but he'll always find that there's a cross, even if there's a circle around. So I guess it still kind of works. And now Roberto can do the next move if he wants to. Yeah. Okay. I think he's back on track. Yes, okay. Okay. It's up to you, Roberto, if you want to draw into. Oh, yeah, thanks. I was gonna ask if he was wanting to try to make it a draw, or if he wanted to make a.
Yeah, Roberto is tryharding in this one.
Yeah, yeah. Okay, robot is not going to give up so easily, I guess. I think. So yeah, the middle one is a cross. So we have to remember. Okay, right move again. Nice. And it's going to end in a draw. So when the draw is coming, I think. Come on, get this cross. I think he's struggling to get the cross right. Oh,
Yeah,
thanks.
now.
Yeah, nice. Okay, it's a draw. Nice. Okay, perfect.
Okay.
And yeah, I should have shown. I guess I will be able to show them later, but these are all the parts that the camera sees. I'll show them in the presentation.
Mhm.
These are like the lines detected, and then the centers of each squares detected. So yeah. So if that's all right, I think I'm gonna go back to my presentation and go on with explaining. Let me clear the board before so that it's
Thank you,
clean.
Roberto,
Okay.
also for
Yeah,
the
thank you,
collaboration.
Roberto. Thank you for playing. Thanks. Okay, I'm gonna go back to the presentation and explain the rest of it. In particular, the problems that I had. So the first main problem that I had was identifying the grid lines. Um, the first approach I used was just trying the OpenCV whole line algorithm on the whole image and try to see where the grid lines for the grid were. But as you see on the left, there's so much noise. So the next logical conclusions was that I was going to have to find a region of interest. So the inside of the board here would be great because the lines are, once you have this portion away from the rest and you just focus on this portion, you can just way more simply identify the lines. So what I did to find out where the tablet was just using a contour analysis. This is just one contour staying. It's just a tablet contour, but if I run this on an image like without any further treatment, it's just gonna draw every contour it finds. So that's why I said before, I said the board was fixed position. That enabled me to find out what the area of this specific contour was and consistently get this specific contour each time. So I know it was around 25,000 square area, and I would just use a little safety interval and consistently getting this only contour as the tablet. Once I had this, I was able to extract the middle part, do a perspective transform to make it all right and not warped. And then I used a Sobel-based filtering for vertical lines, and then another Sobel filtering algorithm, but then for horizontal lines, so with different parameters. I was able to get those results and get much more easier calculation of the grid lines positions. There's another problem that I had, which is kind of related to this one. Before I used the Sobel algorithm, I was using a Canny algorithm or regular edge detection without any vertical or horizontal filtering, and I would get this amount of lines using whole lines algorithm. So I would get horizontal and vertical. And I couldn't get if I had vertical lines, you see all the horizontal noise on this image. And my goal was to find 2 lines for the left vertical line, 2 lines for the right vertical lines, and same for the horizontal lines. So in total, 8 lines. But there's so much noise, and if when I used the whole line once, one set of parameters for this whole line would correctly filter for the horizontal lines, but would be very bad filtering for the horizontal ones. So I would get noise in either direction. So what I used for was just I just separated the 2 detection and used very specific parameters for each O-line algorithm I ran on the image. So one algorithm for vertical lines, and then another one for horizontal lines. And then to get rid of all the noise and just mash all these, because this for example is 1, 2, 3, 4 lines. To mash them all into one line, I use some distance-based clustering to be able to get every lines of the grid correctly. And the last problem I had was with shape detection. I used various methods. Template matching was the first, and I ended up with the last shape detection I used was contour detection and then solidity analysis. So solidity of a shape is just how much void is there in the shape. So how much non-void is there in the shape? So when you take any shape, you have a specific normal area. This is the blue, and then you have a convex hull. If you take the convex hull of this area, it's just the smallest area that's gonna englobe this whole blue area without going into the dips. So in red, the convex hull, in blue, the area. So if you have a base area with a lot of holes, then if you do this area over the convex hull area, so the red area, the more holes you have in your initial shape, the less solidity you will have. So we can easily imagine that for a cross, which convex hull is this red rectangle over here, the solidity is going to be much less than this circle for which the convex hull is just almost a circle. And that was the method I used to separate the circle from the crosses. But sometimes especially when the circle was cropped or mashed or merged with the grid lines and the contour was not perfect, it would get wrong values of solidity and then identify it as a cross. So I needed something to solve this issue. So then the last way I differentiated a cross from circles was just using what I called shape center analysis. I calculated the center of each shape, of each contour I got. And based on how much bright pixels there were in the center, I was able to differentiate crosses from circles, because in a circle you have way less amount of pixels than in a cross. So what I said was, if there's more bright pixels in this center than the threshold, then you can just say this shape is a cross. All right. So let me go into a bit more detail about how my project works. So I talked about it before. These are the 4 parts: the order, perception, the best move, and the trajectory executor. Just to clarify, to deepen a bit, this perception node is getting the information, the image information directly from this camera topic. Then he is computing the game board, publishing this information here with this game board status on this game board status topic, which is identified or registered by this best move node, which is using just a min-max algorithm to compute what the best move will be for the robot. And it outputs this best move. The orders node registers this best move and then generates the move order for the chat directory node, which is interacting with the robot to make it move through the move it to move group. And then you have the robot moving. On the web application part, the way that I was able to make it interact with the system and make the game start, for example, and to make the moves when you needed to manually move the robot, I used this ROS bridge server and published some information in these various topics. So game start if you want to start a game, move order when you want to move the robot, and also for debugging, I was using this perception parameters topic in order to be able to control some computer vision parameters from the web application to live tune these parameters to make the computer vision pipeline more efficient. And on the other side, it's getting information from the system. So the current game board, that's how we could see live the current game board here and the image roll that we saw, and also what the perception system was seeing. So this is the whole system in a bit more technical way. So overall, the results were great in simulation, less great in a real setup. I put it those percentage of success. These are when the vision pipeline is failing at identifying each shape on the board correctly, it will output an error. So the amount of error that it got would give me this success rate. And so it drops by 30% for a real robot, but using some filtering and some buffering and some vote-based output, I was able to mitigate those failures and just output the right condition of the board whenever there was a sufficient amount of right answers to what the board was looking like. And so the robot responds in, I would say, the same amount of success as the computer vision pipeline because it's directly tied to it. And also for the flaws that my project has, my shape detection is not that robust because you can differentiate a cross from a circle, but you couldn't identify what a square, if there was a square or a star. So it's not robust in that sense. And also, I think the code structure could be improved. There are some topics and a lot of publisher that I think I would need to name better. And overall, I think the code structure could be improved. There was also some unsolvable issues. I talked about it before. This is what I saw when I was looking for the biggest contour on the board. And this is why I said the camera and the tablet needed to be fixed position for me for this project, because otherwise I wouldn't have been able to consistently say, I need this area and I know how much squared pixels this area is. And also, I had some issues with the line clustering when the camera was seeing a lot of noise here and there. And I think with a bit more camera resolution, I don't think it's the only factor, but I think it could be easier to solve. So overall, yes, the code structure could be improved. And for the shape detection, to make it more robust, I could use a simple machine learning model and just train it on crosses and circles, and then I would be able to identify the shapes better. And also the robot efficiency, trajectory efficiency could be improved because, as you saw before, the robot kind of goes a bit too deep on the table, and some of the shapes are not perfectly clean. And I think the overall speed could be improved as well of the robot. And I think the line clustering sometimes. So when I merge all the lines into one to get the perfect four grids of of 4 lines of the grid, I think it could be improved. And I think on the real lab side, if I had to give some improvements, ideas. I think an emergency stop for a robot. I don't know how it would be how easy it would be. I don't know how easy it would be to implement it, but I think an emergency stop would be a great, because even though most of the time you can plan and see in advance what your robot will do, sometimes when everything starts to get automated, the robot is moving in some places, and when there's a bug, because usually bugs can happen, seeing the robot and being able to push on a button and make it stop maybe 2 or 3 seconds later could be interesting and to have, I think, for the safety of the setup. But I don't know how hard it is to implement though. And also a higher camera resolution, I think, would ease the detection system, but I think it's also good that it's not 4K, because in real life I don't think the cameras are always going to be 4K in your live perception system. I think it would be quite expensive, and so it's good to have this challenge, but I think it would be easier with a higher resolution. Okay, so that's it for this presentation. Thank you everyone for hearing me, and if you have any questions, feel free to ask. I'll be there to answer.
All right. So yeah, thanks a lot. Let's give an applause to Emeric. Yeah, so really good presentation, Emeric. With a lot of visual support to clearly understand everything. So yeah, now it's time for questions. Then if anyone has any question that he would like to share with Emeric for about his project, so it's the moment. And yeah, so from my side, well, first of all, very interesting suggestion. Like the camera resolution one is easy to implement, actually. And the emergency stop button is something that I really like, to allow the student to have an emergency stop button right from his interface in case that something goes wrong. So that's something that I think we are going to definitely evaluate to include. Yeah.
Okay, nice.
Yeah. And yeah, so well, let me start with a couple questions. So first of all, sorry, about all the manipulation part. So all the trajectories and, well, first a couple of questions about that. So first of all, how did you find out, because this is currently also another improvement that we want to add to the lab, right? Which is finding out the proper distance in the z-axis of the robot to properly draw in the board without falling too short or without over pushing towards the board, right? So how did you find out that? It was trial and test, or?
Yeah. Honestly, yeah, it was all trial and test. Just using the. I think I can show it. Yeah, here. Just mainly using this RViz tool to just lower down the robots just a tiny bit, and check where it is on the board. That was the method I used for clearing the board. I would just slightly, very slightly put down the robot and check whether or not it was clearing the board, and same method for getting the Z. So yeah, I don't think the method I used was the most robust and maybe the most safe, but this is what I used, yeah. So I think making some C++ script to like make the robot go down in specified steps amount. So maybe the steps that you can parameterize on the script. That would be interesting. Like just like a teleop, basically. But going down, I think it would be interesting. I didn't do that. Yeah, I didn't do that.
Yeah. So with the current setup, it's probably the fastest solution to just try a bit step by step and get the exact value, because once you get it, it's not going to change. So what we are planning is to basically put some kind of sensor right in the pencil, so that whenever the pencil does a force against something, you are going to be able to get some kind of output and detect that. But
I was wondering. I just wondered right now because I didn't think of it before. But doesn't the Piper arm has a force sensing on his axis?
No.
I was wondering. Oh no.
No.
Okay.
So yeah.
Mm.
Yeah, that would be great, but unfortunately not. Okay, so we are starting to get many questions. Let me just do another one related to very quickly to manipulation. So for establishing the drawing pattern for the grid, for the circle, for the crosses and all that, did you use Cartesian planning, or what type of motion planning did you use?
I used all Cartesian planning. Yeah. Even for the circle, I just parameterized the trajectory and made waypoints around the circle.
Okay.
Turned out pretty great. I don't remember how much precision I made into the steps, but it turned out pretty great.
Yeah. It's probably the best solution for this, and the one is going to give better results,
I think.
Okay, then let me have a look here at the questions that some people have shared. So, for example, we have Girish here. He's asking, would your project work under any lining? Is your solution lining invariant? And let me ask another question on top of this, because it is related. So during the live demo, we saw that the system, your perception system, had like a fake positive, and it thought there was I think it was a cross or something where it wasn't. And you mentioned that most likely that was, or that's what I understood, that most likely that was because of the shadows being casted into the image. So how would you try to improve your system to protect against these kind of things, and also changes in the lining conditions?
Okay, yeah. I think for this particular problem before, maybe I'm wrong, but because I did some lighting invariant methods. I used actually one for shape detection and another for line detection. So let me just go over what I used, and then I explain my theory for what happened before. I think it's more like a. Well, I'll get to it. For the shape detection, I used the adaptive canny algorithm instead of just having a fixed thresholds. I took the mean brightness of the image so that it would adapt on if there was a shadow casted on the image to get at least the contours for the shapes detection. And for the line detection, I didn't have any light invariant techniques for most of the time. And towards the end, I added, I think, I don't remember if it was Gaussian blur or maybe histogram equalization. I would need to check it again. But I used another. It's not an adaptive canny because I used Sobel for getting the grid lines, Sobel and binary thresholding. But I I'm pretty sure I used another element for light invariant um, filtering, but it's not canny adaptive canny. I would need to check it out again. But I think what happened for the cross was that the it's more about the logic. I think my perception system is going is still working whether or not there is a person on the frame. So Roberto put it. I think it's Roberto. If someone, I don't remember if there was someone in front of the grid or not. But I think my point is I think the false detection of the shape was more about the unrobustness of the still kind of unrobustness of the shape detection. I
Okay,
think
okay.
it got a false shape here. I think the line works pretty good in light invariant conditions. I think it's the shape detect in particular that works bad sometimes. Yeah.
Okay, so
Yeah.
okay, see immerse. Okay, this was okay. Let me go here for a question from Desire, for example. So he's asking, what other methods could be used for to distinguish X's and O's instead of using the convex hull method? So did you evaluate others? You mentioned during the presentation also, like probably machine learning. Did you consider that, or maybe you thought it was too much and it would require too much for this specific project that is time limited?
I think yes. I tried other methods before this center analysis of the shapes. But well, solidity as well, convex hull solidity. I used this as well, and the thing is, I used also before that template matching. Template matching. I tried this on. I was working on simulation at first, and that was a big mistake. I thought I should have tried perception on a real robot right away, but I wanted to try to have the full pipeline on simulation first. So that's why I was working with perception on the simulated board. And I tried template matching there. It was working quite correctly, but still had some failures. So I looked at some forums and I figured out that it was never gonna work for a real situation, but because the way it works is it just takes a cropped pattern and tries to find this pattern on the image. So if it's not perfectly good, it will never find the if the pattern is there on any square. So if I take a cross, it's going to be very hard to find it if it's not exactly the same shape. And if since the real situation with contours changing all the time, it was really hard to. Yeah, I knew it was never going to work, so I needed something else. Solidity, and then this center analysis. I think I stumbled upon machine learning methods along the way, and I think I was already pretty far into making it work for the real setup, and I was pretty close from the end of the month. And I said, okay, it might not be. I might not have the time, yes, to do this machine learning approach.
But
That's why I didn't do it.
you think that probably if you dedicated the time to apply that, that would provide better results?
Yeah, I think so. Yeah, yeah,
Okay.
yeah.
Okay. So yeah, then I think we can leave it here. So thanks a lot, Emeric,
Sorry,
for.
I have something like a
Oh,
final things to present.
okay. Sure. Go ahead.
If it's okay, if it's all right,
Yeah.
if 10 minutes left, okay.
Yeah. Give me a second so that I make sure that we can see your screen. There we go.
Okay. So I was just going to talk about a project that I have, and I'm going to continue it It's this tiny robot I made. It
Wait,
currently,
it's in the camera or?
yeah, sorry, it's in the camera. Can you see it?
Ah, okay, okay. Wait, let me switch then because we are seeing your shared screen now.
Oh, sorry.
Let me
Okay,
switch to.
I can stop the screen.
Yes. Okay. Yeah. Yeah.
Okay.
Yeah. Okay. There we go. We have it now. Yeah.
Let me see because there's some blur. I think you could see it
Yeah,
now.
we can see it. We can see it. Yeah.
So this is the PCB that I made for this tiny robot. On the middle here, how to not blur this out. This is my like the main board. It's an ESP32S3, and there are various things on this PCB like gyroscope here and a double driver for these motors that are going to go here. And it's a base PCB for a tiny robot that I'm gonna try to implement micro ROS on this. So
Okay.
with probably free RTOS. So to just try and see how much of okay, that was a PCB. I'm
Yeah.
just gonna just to see how much load I can put on this kind of restricted system because it's not going to be able to hold everything I put into it. So for now, there's just a gyroscope and some drivers, but I hope to add a little bit more sensors in the future and see how much I can go with it, how far I can go with this tiny setup and micro ROS on it. So yeah, excited to
Oh, really cool. But
take it
it's
to the
going to
next
be
level.
like a wheeled robot, or
Yeah, sorry. Wheel robot with the
we didn't with the board. Yeah.
it's not clear to see
Okay.
with the
Okay.
board, but the board would actually be the kind of the body of the robot, and here
Ah.
are the two holes to put the motors, and the motors are just gonna lay down in the back. Sorry, just gonna lay here and here, and it's gonna be a wheeled robot that's just gonna move here. And this is actually the platform for the robot. It's the same kind of design they use for a competition that's called Micro Mouse.
Yeah.
So they use the PCB for the base of the robot because it's so tiny. There's not very much constraints. I think I'm gonna go with that with this robot. It's gonna be interesting.
Really cool. Really cool. Yeah. Yeah. And you are going to get to learn also about micros and yeah. So keep us updated about the project and
Yeah,
how it
definitely,
goes.
definitely on my GitHub. Something.
All right.
Thanks.
So yeah, thanks a lot, Emeric, for your presentation, for your time, and yeah, congratulations also for reaching the end of the masterclass. It's been a long process, but
Yes.
you've reached the end. So congratulations for that. And
Yeah. Thank you very much. Yeah.
yeah, and yeah, so we'll stay in touch. And if you want to say anything to close the presentation
Yes.
ceremony.
Yes. 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 Just wanted to say big thanks to the whole team. Thank you, Roberto, for playing against the robots. Thank you, Roberto, for all the debugs and everything during the masterclass. And also a big thanks to Desiree for the C++ classes that I took with him. And also thank you very much, Girish, for being there. This whole project, you have been very, very, very helpful to me, and I've learned a lot from all your tips. So thank you very much, and thank you, everyone. Thank you.
All right. Thank
Yeah.
you, Emeric, also for being a great student.
Yeah, thanks.
All right. So yeah, thanks also to all of you that were here doing the presentation. I hope that you enjoyed it, that you have been able to take some knowledge from it and some inspiration too. So yeah, see you in the next final project presentation, which is going to be probably by the end of next month. So stay tuned. And yeah, to all of you, remember, keep pushing your robotics learning. Bye bye.
Bye.